Welcome to The Explainer. Today, we're going to talk about Kubernetes networking, and trust me, if you're a developer, especially a Go developer, this is something you really want to get your head around. We're going to pull back the curtain on how your application actually lives, breathes, and talks to the world inside a Kubernetes cluster.
Okay, so let's picture this. You've just written this awesome Go microservice. It's lean, it's fast, it's perfectly containerized, it's ready to roll. But now comes the big question. How does anyone actually use it? How do you get traffic from the outside world to this brilliant piece of code, and how do you make sure it stays reliable and secure? That's the puzzle we're solving today. So, first things first, we've got to get traffic into the cluster. Let's think of the whole Kubernetes cluster like a giant, secure office building. You can't just walk in any old door, right? You need a main entrance, a proper front door. And in Kubernetes, that front door is a resource we call a service. A service is one of those concepts that's just, well, absolutely fundamental. See, your Go application runs in these things called pods, and they're ephemeral. They can pop up, disappear, get new IP addresses. It's chaotic by design. A service gives you a single, stable IP address that never changes. It's like having a permanent PO box that always knows where to forward your mail, no matter how many times you move. And you've got options for what kind of front door you want. A cluster IP is like an internal memo system. It only works for traffic inside the building. Then there's node port, which is super handy for development. It's like propping open a side door so you can quickly get in and test things. But for the real deal, for production, you're going to want a load balancer. This thing actually tells your cloud provider, hey, build me a proper public-facing entrance, and it just does it. Okay, great. Our request made it past the front door. It's officially in the lobby. But this is a skyscraper, right? There are hundreds of different departments, our microservices. So how does the request know which floor to go to? Well, that's where the cluster's super smart receptionist comes in, the Ingress. An Ingress is basically just a set of rules. It's the receptionist looking at the visitor's badge. Is this request for api.example.com or maybe www.example.com? Is it trying to get to the /login path or the /products path? Based on that info, the Ingress points the request to the right elevator, making sure it gets exactly where it needs to go. And the way this works is actually pretty cool. It's a two-part deal. First, you, the developer, just write down the routing rules in a simple YAML file. But those rules don't do anything on their own. They're just a blueprint. You need an engine to actually read the rules and direct the traffic. That's the job of the Ingress controller, a piece of software like Nginx or Traefik that's constantly watching for your rules and making them a reality. And this is where things get really interesting. This is the question that separates a basic setup from a truly professional senior-level architecture. Simple routing is fine, but modern microservices need more. What if you need to authenticate users at the edge, or protect a service from getting totally slammed with requests? What about all those fancy gRPC services you're writing in Go? This is where we see the big difference between a basic Ingress and a full-blown API gateway. A standard Ingress is like that friendly receptionist who just points you to the right office. An API gateway, though, that's more like the head of building security. It can check your credentials, limit how often you can visit, and even manage protocols way beyond just simple web traffic. It's a whole other level of control. This is exactly why a lot of folks use their Ingress controller as an API gateway with tools like Kong. You get the best of both worlds. You still define your routes using standard Kubernetes files, but you unlock all this incredible power. Suddenly, you can just add plugins for authentication, logging, and even manage that tricky gRPC or TCP traffic your Go services depend on. It's a real game changer. All right, so the request has been routed to the right Go microservice. But that service probably isn't an island, right? It needs to talk to a database, a cache, or some other internal service. How do they all find each other inside this massive, dynamic building? This whole process is called service discovery. And let me tell you, in a world like Kubernetes, where things are always changing, hard-coding the IP address of your database into your API service is a surefire recipe for a very, very bad day. The second that database pod restarts, boom, your application is broken. We need a much smarter system. And Kubernetes has this absolutely beautiful solution for it. It runs its own internal DNS server. Think of it like a company directory. When you create a service, say database service, Kubernetes automatically gives it that predictable name. So now your Go API doesn't care about the IP address. It just says, hey, connect me to database service. And the internal Kubernetes DNS just figures it out. It's magic. So great. Our services can find each other and chat all day long. That's awesome for getting work done, but from a security perspective, it's kind of a nightmare. See, by default in Kubernetes, any pod can talk to any other pod. It's a total free-for-all. We need to hire a security guard for the hallways, someone to check IDs before letting one service talk to another. This is where network policies come in.
A network policy is basically a firewall for your pods. It lets you write really specific rules about who is allowed to talk to whom. It takes that wide open, talk to anyone default and lets you lock it down tight, creating a much more secure environment for your application.
And this brings up a really critical distinction: north-south versus east-west traffic. Your Ingress manages north-south traffic, that stuff coming into and going out of the cluster. Network policies manage east-west traffic. That's the communication between pods already running inside the cluster. You absolutely need both for a solid security posture.
So let's look at the building blocks. You start by selecting the pods you want to protect with a pod selector. Then you decide if you're controlling incoming traffic, outgoing, or both. For example, you could write a rule that says, only pods with the label role API are allowed to connect to my database pods on port 5432. It gives you incredibly fine-grained control.
And here it is. This is probably the single most important best practice a senior engineer can adopt for network security. Instead of trying to block bad traffic, you block all traffic by default. Then you explicitly and deliberately poke holes in that firewall, allowing only the communication paths your application absolutely needs. It's a zero-trust approach, and it dramatically improves your security.
Okay, we've covered a lot of ground. Let's zoom out now and put all these pieces together. We're going to follow a single request on its complete journey, from a user's browser all the way to your Go application and back again.
And now we can see the whole story. A user's request arrives from the internet, hitting our public load balancer. Our receptionist, the Ingress controller, checks the address and routes it to the right department's front door, the service. The service finds a healthy Go application pod and hands off the request. If that pod needs data, it uses the company phonebook, internal DNS, to call the database service. And all along this internal path, our security guard, the network policy, is checking IDs, making sure only authorized communication happens.
So as a Go developer, these are the core ideas to really burn into your brain. Use services for stable addresses. Start with Ingress for basic routing, but be ready to graduate to an API gateway when things get complex. Let Kubernetes DNS handle all your internal communication. And always, always secure your internal traffic with a default deny network policy.
Mastering this flow is a huge step. But the next level of cloud-native development is understanding what happens when things go wrong. How do you debug a failed connection? How do you get deep visibility into the performance of every service? This leads us into the fascinating worlds of observability, monitoring, and service meshes, powerful tools that give you X-ray vision into your running applications. But that is a story for another explainer.